To scientists. Johannes Kepler, 1571 to 1630, was a German astronomer and mathematician. He started working as a helper to the famous astronomer Tycho Brahe in Prague in 1600. After the sudden death of Brahe in 1601, Kepler was appointed as the royal mathematician in his place. Kepler used the observations of planetary positions made by Brahe to discover the laws of planetary motion. He wrote several books. His work was later used by Newton in postulating his law of gravitation. Newton's universal law of gravitation. All the above considerations, including Kepler's laws, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. This figure shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as F is proportional to m1 m2 upon d2, or F is equal to g into m1 m2 upon d square. Let this be equation 2. Here, g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If the two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. In case when the bodies are not spherical and have irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between the two centers of mass. From equation 2, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of an object having uniform density is at its centroid. Why did Newton assume inverse square dependence on distance in his law of gravitation? He was helped by Kepler's third law in this, as shown below. Let's have a look. Use your brain power. Show that in SI units, the unit of g is Newton meter square per kg square. The value of g was first experimentally measured by Henry Cavendish. In SI units, its value is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Uniform circular motion or magnitude of centripetal force. Consider an object moving in a circle with constant speed. We have seen earlier that such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle. What is this force called? This force is called the centripetal force. If m is the mass of the object, v is its speed, and r is the radius of the circle, then it can be shown that this force is equal to F is equal to mv square upon r. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equal to mv square upon r, where m is the mass of the planet, v is its speed, and r is its distance from the sun. The speed of the planet can be expressed in terms of the period of revolution, t, as follows. Speed is equal to distance travelled upon time taken. The distance travelled by the planet in one revolution is equal to perimeter of the orbit 2 pi r. R is equal to distance of the planet from the sun. Time taken is equal to period of revolution equals t. Now v is equal to distance travelled upon time taken, which equals 2 pi r upon t. F is equal to mv square upon r, which equals m into 2 pi r upon t whole square upon r, which equals 4 m pi square r upon t square. Multiplying and dividing by r square, we get F is equal to 4 m pi square upon r square, which equals r cube upon t square. Now, according to Kepler's third law, t square upon r cube is equal to k. So, F is equal to 4 m pi square upon r square k. But 4 m pi square upon k is equal to constant. Therefore, F is inversely proportional to r square. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. This is possible because of the huge masses of planets, stars, and other constituents of the universe. Use your brain power. Is there a gravitational force between two objects kept on a table or between you and your friend sitting next to you? If yes, why don't the two move towards each other? Yes, there is a gravitational force between two objects kept on a table or between you and your friend sitting next to you. But the gravitational force exerted by Earth on both objects or friends is much greater than the attraction between two. Hence, the two don't move towards each other. Let's have a look at some solved examples. Example 1. Mahendra and Virat are sitting at a distance of 1 meter from each other. Their masses are 75 kg and 80 kgs respectively. What is the gravitational force between them? Now, given we have R is equal to 1 meter, M1 is equal to 75 kgs, M2 is equal to 80 kgs, and G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. According to Newton's law, F is equal to Gm1 M2 upon R square. Let's substitute the values. F is equal to 6.67 into 10 raised to minus 11 into 75 into 80 upon 1 square Newton, which equals 4.002 into 10 raised to minus 7 Newton. So the gravitational force between Mahendra and Virat is 4.002 into 10 raised to minus 7 Newton. This is a very small force. If the force of friction between Mahendra and the bench on which he is sitting is 0, then he will start moving towards Virat under the action of this force. We can calculate his acceleration and velocity by using Newton's laws of motion. Example 2. In the above example, assuming that the bench on which Mahendra is sitting is frictionless, starting with 0 velocity, what will be Mahendra's velocity of motion towards Virat after 1 second? Will this velocity change with time and how? Given force on Mahendra, F is equal to 4.002 into 10 raised to minus 7 Newton. Mahendra's mass, M, is equal to 75 kgs. Now, according to Newton's second law, the acceleration produced by the force on Mahendra is equal to M, which equals 75 kgs. A is equal to F upon M. Substituting the values, A is equal to 4.002 into 10 raised to minus 7 upon 75, which equals 5.34 into 10 raised to minus 9 meter per second square. Using Newton's first equation, we can calculate Mahendra's velocity after 1 second. Newton's first equation of motion is V is equal to U plus AT. As Mahendra is sitting on the bench, his initial velocity is 0. That is, U is equal to 0. Assuming the bench to be frictionless, V is equal to 0 plus 5.34 into 10 raised to minus 9 into 1 meter per second. So V is equal to 5.34 into 10 raised to minus 9 meter per second. Mahendra's velocity after 1 second will be 5.34 into 10 raised to minus 9 meter per second. This is an extremely small velocity. The velocity will increase with time because of the acceleration. The acceleration will also not remain constant because as Mahendra moves towards Virat, the distance between them will decrease, causing an increase in the gravitational force, thereby increasing the acceleration as per Newton's second law of motion. Use your brain power. Assuming the acceleration in example 2 above remains constant, how long will Mahendra take to move 1 centimeter towards Virat? Collect information about high and low tides from geography book. Observe the timing of high and low tides at one place when you go for a picnic to a beach. Take pictures and hold an exhibition.